Hello, I am Brandon Matthews from the Australian Research Centre for Interactive and Virtual Environments at the University of South Australia. I am presenting our paper Shape Aware Haptic Retargeting for Accurate Hand Interactions. Haptic retargeting enables the reuse of simple objects to provide passive haptic feedback in virtual reality. Previously, this has been applied to remapping between virtual and physical interfaces, mapping larger surfaces onto elements of the virtual environment, and reusing simple props like cubes. Say we have a single physical cube, yet there are multiple virtual cubes within a virtual environment the user wants to grasp. We can introduce an offset between the user's real hand and the virtual hand they can see, redirecting the user to reach out and grasp any of the virtual cubes while actually grasping the one physical cube. Several variations of this illusion exist. In this paper, we primarily focus on the body warping algorithm and its later extension on-the-fly retargeting. In most haptic retargeting implementations, the target, origin, and in particular the user's hand have been represented by a single position in 3D space. For example, the center of a target or the tip of the index finger. As shown in the top right, if the interaction position on the hand and the target position are not perfectly aligned on contact with the physical proxy, a visible error can be seen. This has meant interactions are typically limited to only one finger to ensure accuracy. Some previous research has implemented an understanding of the target shape, including the sparse haptic proxy system and Zhao and Follmer's functionally optimized method for continuous retargeting. These methods consider the shape of the target or origin. However, no previous method has considered the shape of the hand to enable interactions with any finger or any part of the hand. The motivation of this research was to explore and develop an extension to on-the-fly and other haptic retargeting algorithms that can provide accurate whole-hand interactions with retargeted proxies of any size and complexity. We present Shape Aware Haptic Retargeting. This is an extension to existing haptic retargeting methods that ensures a user's retargeted virtual hand always contacts the virtual target in the same relative position as their real hand contacts the real target. Likewise, the hand will always be realigned regardless of which part of the hand contacts the origin. We generalize the distance calculation in state-of-the-art haptic retargeting to consider the shortest distance from any hand representation to any target representation and to any origin representation. We formulated 3 shape approximations that can represent the physical hand, target, and origin with varying degrees of accuracy. These approximations are multi-position, primitive, and mesh geometry. They could take other forms, but critically we must be able to compute the shortest distance between them. The multi-position representation leverages multiple key positions on the hand, target, and origin. The closest pair of positions is found and provides the distance for the retargeting algorithm. The primitive representation leverages the mathematical representations of primitive shapes. The hand, target, and origin are represented by one or more of these primitive shapes, and the shortest distances are found and become the distance for the retargeting algorithm. In the mesh distance method, the hand, target, and origin are represented by a triangulated mesh. We then find the closest point on each mesh by testing distances between each triangle pair. To provide real-time performance, this was implemented in a Unity compute shader running in parallel on the GPU. We chose this brute force approach for 2 primary reasons. Firstly, the hand is a concave mesh and deforms in real time, limiting the applicability of other mesh optimizations. Secondly, this method is simple to implement in parallel for better performance, and computation of the deformed mesh can also be done in parallel. So which method produces the most accurate interactions? We conducted 4 simulated evaluations to quantify the performance of shape-aware haptic retargeting. The simulations were selected to represent a variety of interactions and configurations. To measure the performance, we measure the distance between the actual hand position and the expected hand position in each simulation. We tested 3 target types and 5 hand types. The target types are position, primitive, and mesh, and the hand types are palm, index, fingertip, all fingertips, primitive, and mesh. For each simulation, the hand is pre-posed for the interaction. In the cube grasping simulation, the hand grasps a 5 cm cube and the error is sampled upon completion of the grasping. In the button pressing simulation, the hand is animated to press the button using the tip of each finger and thumb. The error is sampled 1 time for each press. The complex object simulation introduces a more complex object, specifically the Utah teapot. This is a concave mesh that can only be closely approximated by multiple primitives. The error is sampled when the hand grabs the teapot handle. Across the board, the primitive and mesh hands performed the best in these simulations, showing an error of 0 for the primitive and mesh targets in all cases. Particularly in the button pressing simulation, we see that the multi-point primitive and mesh hands enable accurate interaction with all 5 fingers. In the continuous interaction simulation, the hand traces the top edge of a box using the tip of the index finger, emulating an exploration type interaction. The error is sampled every 50 milliseconds during the interaction to plot the change in error. In the continuous interaction simulations, the primitive and mesh targets produced an error of 0 throughout the whole interaction for all hands beside the palm, creating a consistent square path along the edges. The palm hand and the position target produce visible variations in the path, and at one point the error exceeds 30 millimeters. A similar interaction using any other fingers would show similar although smaller variants for the index finger hand on the mesh and primitive targets. In conclusion, we developed Shape Aware Haptic Retargeting, an extension to existing haptic retargeting methods that enables interaction between all parts of the user's hand and the target. Simulated evaluations showed the mesh and primitive representations both provide accurate interaction with the entire hand and the entire target. Primitive is more performant, however it is less accurate to the true shape of the target and hand. And multi-position may have uses for remapped physical virtual interfaces to enable interaction with any finger on a smaller target. Thank you for watching, and please feel free to contact me for more information.